We think time controls us, but what if it's the opposite? While you believe you're living each second, have you ever wondered if an unseen force is actually guiding? What if someone is watching the past, the present, and the future all at once? What you're about to learn will reveal that time is a far darker secret than you ever imagined. Before watching the video, don't forget to subscribe and turn on notifications by tapping the bell. Hello everyone, I'm Omniverse. Where does time begin? Where does it end? Before the Big Bang? Did time even exist? Or will it ever end? When our solar system reaches its final days? When we are long gone? Will time still exist? Is time something that flows independently of everything? Of all of us? Of all matter? Like a straight line? According to the fathers of classical physics, Galileo, Newton, and others, the answer is yes. Time is absolute, unchanging, constant, and flows independently of all things. Especially when the phrase absolute time is mentioned, everyone immediately thinks of Newton. But there was a young man working in a patent office in the city of Bern. Remember him? Do you know what he once wrote in his journal? Newton, I'm so sorry. With that sentence, he was basically dissing Newton, Descartes, Galileo, Maxwell, and dozens of other names who shaped history. He was saying, "Gentlemen, I'm sorry, but that's not how it works." That rebellious young man was Albert Einstein, a man who, as a student, once said, "I don't care about this phenomenon or that phenomenon. I want to know how God thinks. The rest is mere detail to me." A man who, even an hour before his death, picked up his notebook and pencil, trying to write the final step needed to understand the mind of God, the theory of everything. We'll talk a lot about Einstein. A lot. His brilliance, his flaws, everything. I have so much to tell you about his life and his way of thinking. But today, we will talk about time. And to understand time, we need to travel back to the place where everything began. Don't worry. We're not going all the way back to Greek mythology or ancient philosophers. Although Aristotle and Copernicus pondered these ideas, we're going to the era when time was studied scientifically for the first time. Let's go to the 16th century. What a century it was, right? Galileo, Newton, Barrow, Descartes. An age of enlightenment that extended into the 17th century. And humanity began studying time with Galileo Galilei. With Isaac Barrow and Isaac Newton, the concept of time reached the form that would be accepted for centuries. According to all these scientists, time, just as we mentioned earlier, was absolute and universal. This definition of time is also called Newtonian time. This absolute time was the same for everyone, flowed at a constant rate throughout the universe, could be measured but could not be perceived. Newton believed that time and space were completely separate components of objective reality. And he believed that even if everything in the universe vanished, time itself would continue to exist on its own. What did Shakespeare say? All the world's a stage. And according to Newton, time was the only thing on that stage that never changed. While explaining gravity and the laws of motion that changed the world, time was the one thing he left untouched, constant and absolute. And that's why we said at the end of the previous video, there was a problem. A problem Newton could not solve in his entire lifetime. A problem he believed must be the work of God, something beyond human understanding. The clearest sign of this problem was hidden in the motion of the planet Mercury. Newton's laws could calculate everything perfectly, from the fall of an apple to Earth's orbit, but Mercury refused to obey. Its orbit kept shifting. This is where Newton said, "It must be God's work." Some scientists even hypothesized a hidden planet we couldn't see, named Vulcan, to explain Mercury's strange orbit, because only the gravitational pull of another planet could account for this anomaly. But it didn't exist. It simply didn't. There was absolutely no explanation for why Mercury's orbit defied all the laws. And as long as time remained absolute, there never would be. Now I'm going to ask something from you. It's very, very difficult. I know. But I want you to forget everything you think you know about time. Forget how time passes. Forget the idea that it flows as a straight line. Forget the idea that we live and die on a single timeline. Forget that time is the same for everyone, everywhere, regardless of how or where you live. Forget it all, because we must completely destroy this perception, because it's wrong. All of it is wrong. Who says this? First, Wilhelm Leibniz. For Leibniz, there were events that occurred before, after, or simultaneously with one another. Time was simply the way our minds organized these relationships. Then, independently, and from a more philosophical point of view, Immanuel Kant joined in. Kant argued that time was not something that existed by itself, nor a sequence of relationships between things that existed by themselves. According to Kant, time was simply the way our minds organize the experiences we have. Kant argued that things that exist independently of us, outside our minds, do not actually exist in time. But all these debates would eventually be settled by Albert Einstein. In 1905, known as the miracle year of physics and of Einstein himself, he published 4 groundbreaking papers, including the theory of special relativity. And after more than a decade of relentless effort, he published the general theory of relativity as well, securing his place in history forever. These are not ideas that can be summed up in a single sentence. We'll go into the details later, but let's not lose our focus. We were talking about time. What is time? This question bothered Einstein more than anything else, despite him being a huge admirer of Newton. Because once Einstein saw Maxwell's equations, he became certain of one thing. There is only one constant in the universe: the speed of light. No matter where you stand or how you look at it, light always moves at the exact same speed. And if that's true, then something in Newton's laws had to change. Something could not remain constant, especially time. Time could not be absolute anymore. Let's continue with an example, a catastrophic one, a scenario where the sun suddenly disappears. Imagine that one day the sun vanishes instantly, without any warning. If we analyze this scenario using Newton's law of gravitation, here's what would happen. Earth would immediately fly out of its orbit and drift into space, instantly. Because in Newton's model, it's as if there's a rope between 2 objects exerting gravity, as if the larger object is reaching out and pulling the smaller one with a constant, instantaneous force. But according to Einstein, this is impossible, because the only constant in the universe is the speed of light, and nothing can exceed it. It is the universal speed limit. Sunlight takes about 8 minutes to reach Earth, and since gravity also propagates at the speed of light, if the sun disappeared right now, we would live for 8 full minutes without noticing anything at all. After that, well, that part is not very pleasant. We'll talk about it later. This discovery was one of the most important breakthroughs in the history of science. And the strange thing is, we could have lived our entire lives under Newton's laws without ever realizing the mistake. Because this is not something we can perceive in daily life. Newton's model was accurate enough, about 99% correct when describing the motions of objects in our solar system. But that remaining 1%, which meant nothing to us, was a problem for people like Einstein. And in his view, everything must have an explanation. So how did Einstein reach this conclusion? He actually realized it when he was just 16 years old. Einstein was famous for his thought experiments. He could visualize any situation in his mind and extract answers from it. One of these early thought experiments involved a train and two observers, one inside the train and one standing outside looking at it. The train is moving at an extremely high speed. Now imagine this. Behind the train, there are two trees standing 100 meters apart, and lightning strikes both trees at the same time. According to Einstein's thought experiment, the person standing outside the train sees both lightning strikes happen at the exact same moment. Both trees are struck simultaneously. But from the perspective of the person inside the fast-moving train, the lightning first strikes the tree in front, and then, after a brief delay, the tree behind. Now, is relativity starting to make a little more sense? The same event, two different observers, two different times. How is that possible? Let's try another example to strengthen the idea that the speed of light is constant. In everyday life, speed is relative. We measure it by adding or subtracting motion depending on our reference point. Imagine two cars driving side by side, both moving at 60 kilometers per hour. From inside each car, the other appears motionless. Its speed relative to you is 0. But if one car speeds up to 80 kilometers per hour, then from the perspective of the 60 kilometers per hour car, the other is moving at 20 kilometers per hour. That's the basic rule. But this rule breaks completely at the speed of light. For example, the exact speed of light is 299,792,458 meters per second. Let's round it to 300 million meters per second for simplicity. Now imagine we build a spacecraft capable of traveling at 150 million meters per second, half the speed of light, and we fly alongside a beam of light. Normally, from this spaceship, you would expect to measure the speed of that light beam as 150 million meters per second, right? But no. Whether you measure it at rest or while moving at half the speed of light or even at 90% of the speed of light, you will always measure the speed of light as exactly 299,792,458 meters per second. How is that even possible? Let's explain it, or at least try to. You've surely heard of the most famous equation in physics, E equals mc squared. Here, E is energy, m is mass, and c squared is the speed of light squared. When Einstein first wrote the equation, he actually arranged it as m equals E divided by c squared, meaning that energy and mass can be converted into one another. In fact, brace yourself, mass and energy are essentially the same thing. Everything you can touch, see, or observe is actually energy in a different form. You are made of energy, and a tremendous amount of it. For example, take a simple paperclip. If every atom in that tiny paperclip could be fully converted into pure energy, the result would be equivalent to an 18 kiloton TNT explosion, nearly the same force as the bomb dropped on Hiroshima. We'll talk about this in detail later, but without drifting off topic, this equation shows us something crucial. As an object's speed increases, its energy increases. And because energy and mass are interchangeable, its mass increases too. And as it approaches the speed of light, the energy required to keep accelerating it becomes infinite. Yes, infinite. And therefore its mass would also approach infinity. That is why nothing with mass can ever exceed the speed of light. The real mindbender is this. In the physics we're familiar with, speed times time equals distance. But when you plug the speed of light into this equation, the physics we know simply stops working. Because the speed of light is constant, something else must adjust. That something is time and distance themselves. Let's tie this together with one final example. Imagine two twin astronauts named Chris and Angelina. They join an experiment designed to prove this law. Chris stays on Earth. Angelina boards a spacecraft capable of reaching 99.997% of the speed of light for a one-year mission. Suppose they are both 30 years old at the start of the journey. After Angelina completes her one-year trip, she returns at age 31. But Chris, who remained on Earth, will be 81 years old. For someone traveling at such an extreme speed, time slows down dramatically. And Chris and Angelina would likely become the first twins in history with a 51-year age difference. And by the way, this isn't just theory. It was actually tested and confirmed in 1971 in the real world. In the experiment known as the Haffel-Keating experiment, 2 of 3 synchronized atomic clocks were placed on airplanes flying in opposite directions. One eastward, one westward. The third clock stayed at the airport. When the planes landed and the clocks were compared, they were no longer synchronized. The clock on the eastbound plane was behind the stationary airport clock by 59 billionths of a second, while the westbound clock lagged by 273 billionths of a second. Hard to wrap your mind around, isn't it? The human mind resists accepting it. Yet a single example from everyday life may be enough to show why this theory matters. Take the GPS system, for instance. Satellites in orbit move at extremely high speeds, which causes very tiny time differences. And these differences must be constantly corrected. Otherwise, when you checked your location on Google Maps, your position could be off by kilometers, and nothing on Earth would appear where it actually is. And everything I've talked about so far has only been a very, very short summary of Albert Einstein's special theory of relativity, published in 1905. You may have noticed I haven't even mentioned gravity or the general theory of relativity yet, or the realm where even Einstein struggled, the world of quantum mechanics. We're only just getting started. All these laws, theories, and examples. At some point, a person naturally wonders, what does any of this even mean for my daily life? I think about that sometimes too. It all feels so difficult to grasp. You want to give up. But then I find myself thinking about the universe again, and about that energy I mentioned earlier. The idea that all of us, everything, is made of energy. That time itself might be nothing more than an illusion. That everything, our perspective on events, our problems, worries, joys, sorrows, everything is relative. Everything changes depending on the point of view. When I think about all this, I realize physics is actually talking about me. And it changes my entire perspective on life, on the universe, on everything happening around us, on society, politics, matter, psychology, and on myself. It transforms the way I see the world from the ground up. So, let's see what we'll learn about ourselves in the next video. Shall we meet again at the first opportunity? Until then, take very good care of yourself. And as always, I'm glad you exist. Much love.